Welcome to the ePath Shala lecture series in computer science. We are dealing with the course computer architecture. This module discusses the execution of a complete instruction, the data path implementation. So, the learning objectives are to discuss how an instruction gets executed in a processor and the data path implementation using the MIPS architecture as a case study. So, we have already discussed the MIPS architecture. We will quickly do a review of the MIPS architecture. So, the MIPS architecture looks at a 32-bit byte addresses aligned. It uses only load store instructions and with displacement addressing for memory operations. It uses the standard data types. It has 3 fixed length formats. It has 32 64-bit general purpose registers with R0 register always having a value of 0, you can't change that. It has 32 floating point registers, it has a floating point status register and no support for condition codes. And if you look at the addressing modes, there are only 3 addressing modes supported. You have immediate addressing, you have displacement addressing used for load and store instructions for memory related operations, and it uses a register mode or register addressing for ALU operations. Recall that the MIPS architecture is a load store architecture or a register ISA, where all arithmetic operations can be done only on register operands, and load and store are the only instructions which can involve memory operands. So, if you look at data transfer instructions, you have a load store word, load store byte, half word, signed as well as unsigned. Similarly, you can do floating point data transfers. You can transfer data between general purpose registers and floating point registers. And if you look at the arithmetic operations, you have addition, subtraction, signed and immediate operands, multiplication, division, signed as well, and logical operations like AND, OR, XOR, immediate value and shifting operations. And if you look at the control operations, branch on equal to or not equal to 0, you have some of these branch instructions and all the floating point operations indicated here, out of which we are only going to look at a subset of these instructions and look at how the data path gets implementation. And again a recap of the 3 instruction formats that we have already looked at: an I type instruction format, an R type instruction format and a J type instruction format. So, when you look at an I type instruction format, you have the opcode. Remember, in all these formats it has a standard 32-bit template. All the formats has a 6-bit opcode part, which is the first part of your instruction, 32-bit instruction. You have an RS register specifier for the source operand in all these places, the register specifier for your destination operand. So, if it is an immediate instruction, you are going to add the source to the immediate operand and the result is going to be stored here. For a register R type of instruction, you need to have 2 register operands. So, RS is one register operand, RT is another register operand, and because you have 32 registers, you need 5 bits for all these register specifiers. This is the destination register. It is a, for example, it is an add R1, R2, R3. So, 2 source registers and 1 destination register. This is used for special functions like shifting and all that. This specifies the ALU operation, which we will discuss later on. And if it is a jump instruction, again it follows a 32-bit format. It has a 6-bit opcode in the same position and it has a 26-bit offset value, which will have to be added to your PC after doing a shift of 2 bits. So, these are the standard formats that we are going to look at when we look at your MIPS instruction set. And we will examine 2 MIPS implementations. So, first of all, we look at a simplified implementation of the MIPS instruction set, and then we look at in a later discussions, we look at a more realistic pipelined version, and we look at a simple subset which shows most of the aspects of what we are trying to cover. So, we will only look at memory reference instructions, load and store. We will look at arithmetic operations like add, sub, AND or OR, and we look at control transfer instructions, which is a branch on equal to or a jump. These are the 3 different types of instructions that we look at. So, when you look at any instruction execution, you know that these are the steps involved in any instruction execution. You will have to fetch the instruction from memory, you will have to decode the instruction to find out what is to be done, and then depending on what the decoding says, where the operands are available, you will have to go ahead and fetch the operands, then you will have to execute the instruction, and then you will have to write the result. So, when you look at an instruction execution and the instruction fetch as part of the instruction execution, how do you fetch the instruction from memory? You know, the program counter always has the address of the next instruction to be executed. So, use the program counter to address the instruction memory and fetch the instruction from memory. And in the case of your MIPS architecture, what happens is, because all your instruction formats are of the same type, they have same size, everything is a 32-bit instruction. To fetch an instruction, it takes the same amount of time. Suppose if you have a different architecture which has different lengths of instructions, the fetch time is going to be different. And remember that MIPS uses a fixed length encoding, that is, it uses 32-bit instructions for all formats. It has opcodes available in the same place, it has the register specifiers available in the same place, and so on. So, that is called fixed length encoding, that is a type of encoding which we have already discussed. Now, because of this fixed length encoding and the registers being available in the same position, now as the decoding of the instruction takes place, you can also look at the register specifiers, use the register specifiers and go ahead and read the registers from the register file. And the register numbers indicate the register specifiers are indicated in the register numbers, and go ahead and read the register file. So, the first part of your instruction execution is your instruction fetch, that happens uniformly, and then you go in for the decode of the instruction, where it is not only the decoding that happens, you also read the register contents from the register file, because it uses fixed length encoding. So, forget about whether you are going to use these register contents or not. If at all you are going to use these register values, these are the registers that you have to read, and there is nothing wrong in reading these registers. So, you go ahead and read these registers. So, that is what happens in the second part. The third part is, you have decoded the instruction, now you have read the register operands. Now, once the decoding has been over, you know what instruction it is. So, depending on what instruction it is, depending upon the instruction class, you will have to do different operations now. So, you will have to use the arithmetic and logical unit. So, use the ALU to either calculate the arithmetic result. It may be an arithmetic instruction, it may be an add instruction, for example. So, you will have to do the addition operation, or it may be a load or a store instruction. For a load or a store instruction, the only addressing mode that is used is displacement addressing. And if you recall what displacement addressing is, you have a displacement component given, and you have a base component which is a register specifier which is given. So, in order to find out the effective address of the memory location, you will have to add the register component, which is the base component, to the displacement value. So, this memory address calculation is done for load and store in the ALU. And if it is a branch instruction, which is the third type of instruction, for a branch instruction you will have to calculate the target address. Again, the way the branch addressing mode is specified for your target address is, you have the displacement given along with the instruction. It is relative addressing, it is PC relative addressing. So, the branch target address can be calculated by finding out the displacement and adding the displacement, so to the PC value, that is the branch target address. So, as far as depending upon what instruction is to be executed, you either perform an arithmetic operation, or you perform the effective address calculation, or you calculate the target address. To calculate the target address and to do a branch, you have to do a condition evaluation, because only if the condition is satisfied, you will have to do the target address calculation. And condition evaluation in the case of MIPS is just comparison of registers. So, you have already read the registers. So, the ALU will check whether the registers have the same values, that is, check for 0 condition or not. So, that is part of the branch calculation. So, the condition is evaluated, and if the condition is satisfied, then you will have to change the target address. Now, once you do all this, the fourth step is accessing data memory for load and store. Now, this step is actually necessary only for memory related instructions, which is load and store. All other instructions will never perform a memory related operation. So, all other instructions do not have to perform this step. For a load or store instruction, the effective address has already been calculated. So, using that effective address, you will have to access data memory. So, if it is a load instruction, then use that memory address and bring the data to the processor. If it is a store instruction, you already have the memory address, use the data that is available in your register, which is the data to be stored onto memory, and go ahead and finish your load. And then now you will have to get ready for the next instruction, because you have already calculated the target address for a branch, and for all other cases it is just the next instruction that is to be executed. So, it is PC plus 4. So, either increment the program counter with 4, it is 4 because every instruction is a 32-bit instruction, which is a 4-byte instruction, and the memory is organized as bytes. So, you either have to do a PC plus 4, increment the PC, so that it is pointing to the address of the next instruction, or you will have to load the target address into the program counter if it is a branch instruction. So, these are the basic steps that will have to be done for any instruction. Now, this is a brief overview of your CPU. We will keep refining this as we proceed. So, you have the program counter here. The program counter value is used to address the instruction memory here. So, the instruction memory is used here to increase the program counter value is used to address the memory here, instruction memory, and you get the instruction from here. So, this instruction is decoded here. Once you decode it, you have the register specifiers available. So, read it from the register file and store it here. So, this is the register file, you store all the register values here, and then you go ahead and do the other operations. So, it passes on to the ALU unit for arithmetic operations, and then it passes on to the data memory for your load or store instructions, and then you have to pass on the result if it is a load instruction. And as far as this part is concerned, the PC value, the incremented PC, the current PC value has to be given here. You have to add 4 to this to get the incremented PC value, or if it is a branch instruction, use this PC value, and the target address, the displacement value that you have here has to be added here, and that gives you the new target value, which will have to be loaded into your program counter. Now, if you look at the earlier diagram, this is your primitive flow diagram, where we have just indicated it by means of points here. So, it is either the PC plus 4 value that will have to be loaded into your program counter, or it is PC plus 4 plus the branch displacement which will have to be added. That is one point. Similarly, if you look at this point, what will happen is, if it is an arithmetic operation, the result of the arithmetic operation comes here, and if it is a load instruction, the data that is to be loaded into your register file comes from the data memory. So, you have a combination here, this wire and this wire, which is to be loaded. And similarly, here the instruction, if it has an immediate component, that immediate component is going to be sign extended, and it is given here, and the register value is given here. So, you have one of two values given here. Now, when you look at all this, it is not possible to just connect wires like this. So, you have to use a component for it, which is your multiplexer. So, you just bring in a multiplexer here. So, your multiplexer here shows how this is multiplexed. So, you have two paths here, one is PC plus 4 and the other one is PC plus 4 plus the displacement. So, you have to put in a multiplexer here in order to decide which one to choose, the control signal to the multiplexer which will decide which one to choose. Similarly, I have 2 points here, I have one coming in from the ALU, the other one coming in from the data memory. So, this will tell you what is to be chosen, and similarly here I have either the immediate component given here or the register specifiers value, register value given here. So, you will have to select one of them. So, wherever you have to join wires like this, you will have to use multiplexers. And then it is not just enough if you show this data path, you will also have to have control signals. So, the moment you introduce multiplexers like this, you know that you will have to have control signals for all these multiplexers. And apart from these control signals, you know that you also have to have control unit that is introduced. So, this control unit will tell you what are the various control signals that are to be generated. For example, when you have to write into registers, you will have to initiate your register write control signal. If you have to do a memory read operation, I will have to initiate a memory read operation. If I have to do a memory write for a store instruction, I will have to activate my memory write control signal. You will have to decide what ALU operation has to be given. Anyway, we will discuss about all these control signals in detail as we proceed. This is just to give you a feel of what are the various control signals, and you can't just ignore the control signals. So, the instruction, when it is decoded, that instruction information is given to the control unit, and depending on what type of instruction it is, the various control signals are generated, and these control signals will be applied at the appropriate times in order to control the flow of instruction in the instruction unit. Now, if you look at the logic design basics, all of you all are familiar with this. We will just quickly go through this. You know that low voltage is 0, high voltage is 1. You have one wire per bit, and when you have multiple bits, you have multiple wires. You have when you have a combinational element, it only operates on the data, operates on the data and produces an output which is a function of just the input. Whereas, if you have sequential element, it is capable of storing the information. These are some examples of combinational circuits, and this is a sequential element where you are talking about a flip flop which is capable of storing information, and it is edge triggered. Similarly, this shows you a register where you have a series of flip flops and a register with a write control. So, whenever the write signal is activated and the clock signal is given the appropriate transition, a write operation happens. And you have a clocking methodology which decides when the clock signals are generated. So, if you look at a sequential circuit, you have the combinational circuit deciding what is the output that is to be given to the state element, which in turn decides the next state of your circuit. Now, if you look at the data path that we are going to look at, the data path is nothing but the elements that process the data and addresses in the CPU, and this consists of your registers, your ALUs, your muxes, memories, and so on. And now, we will build a MIPS data path incrementally by refining the overview design that we looked at earlier. So, look at your instruction fetch. So, for an instruction fetch, PC is a 32-bit register. So, use this PC, give the address to your instruction memory, get the instruction, and as part of your instruction fetch operation, also take your PC value, add 4 to it, so that you get the next address. So, this is part of your instruction fetch, fetching your instruction and also appropriately incrementing the program counter, not accounting for branches for the time being. I am just always incrementing it by 4. So, if it is an R format instruction, you have to read 2 register operands, and you have to perform the arithmetic or the logical operation, and you will have to write the register result. So, if it is an R type of instruction, you know that you have 2 register specifiers. So, 5-bit specifies one of the register operands, another 5-bit specifies the other register operand. This tells you where you have to write the result into, and this is the data that has to be written, which will be generated later on, and you will have to write here. So, the registers, the 2 register values that you read are given as 2 outputs here, and if you have an immediate component, that immediate component is taken and sign extended, and the control signal that is given for your registers is a register write control signal, and register read of course to read, and the data is generated here. So, this is part of your R format instruction. And what will happen for an ALU operation is, so the ALU will take in 2 inputs, one from your register specifier here, the other one again from a register specifier or an immediate operand that is sign extended. So, the ALU will perform operation. What operation it will perform will be decided on the ALU operation that is given here, and then it will produce the ALU result. If it is a load store instruction, you will have to again read the register operand, that will give you the address, part of the address, that is the base address, and the displacement component will give you the offset that is to be added. So, adding both of them will actually give you the effective address. So, sign extension happens to the immediate component. The immediate component is taken, it is a 16-bit value, it is sign extended to produce a 32-bit value, that is the sign extended value. And when you have to perform a memory read operation, you either give a memory read control signal, and if it's a store instruction, you will have to perform a memory write operation. So, you will have to give a control signal called memory write. So, the memory unit, you will have to give the address as the effective address. If it's a write data, you will have to give the data that is to be written, and if it's a load instruction, the data that is read is produced outside the memory unit. So, this is what happens for a load store instruction. If it's a branch instruction that you will have to handle, then you again have to read the register operands and you will have to compare the operands. In the MIPS architecture, recall that you are not using condition codes. Registers are just compared to find out whether they have the same content or different content. So, it is just checking for 0, checking whether they have the same values or different values. And you know that the register operands are already read during the decode stage itself. When the decode happens, the registers are also read. So, you can just compare the operands. So, use the ALU, subtract the 2 operands and check whether the result is 0 or not. So, the 0 output is produced from the ALU, the 0 output is nothing but the result of your condition evaluation, and then you will have to calculate the target address. If the condition is satisfied, you will have to calculate the target address. So, in order to calculate the target address, you will have to sign extend the displacement. So, the displacement which is given as the last 16 bits will have to be sign extended to form a 32-bit value, and then that will have to be shifted 2 places, because a word in a MIPS architecture is a 4-byte word, and in order to support the word displacement alignment of a word, you will have to shift it left by 2 places and then add the PC plus 4 value. You have already incremented the PC to PC plus 4. To that PC plus 4, you add the relative address here, that will give you the new target address. So, this is the indication that is given for your branch instruction. So, you find that this is the base address that is read, the displacement value is given here, the displacement value is sign extended here, and that sign extended value is given to this unit. You do a shift left operation and then you do a shift left operation and then that shifted value is given here, PC plus 4 is given here. This does the addition operation and gives you the branch target. Now, it is either this branch target or the PC plus 4 value that will have to be loaded into your program counter. The shifting operation just reroutes the wires, that is all. The sign bit, the sign extension is nothing but the replication of the sign bits, and the ALU operation, the ALU unit here decides whether the comparison of the 2 registers is the same or not, the 0 condition is satisfied or not. Now, if you look at the elements that compose the data path unit, you will have to understand that the data path executes one instruction in one clock cycle. So, you have multiple operations that will have to be done for every instruction, and all of them, if you assume that they happen in one complete clock cycle. Now, each data path element can only do one function at a time. So, you can't expect it to do multiple operations, and hence we cannot use a same functional unit to do multiple operations. So, we need separate instruction and data memories. For example, when you are looking at instruction fetch, you are going to use the instruction memory. When you are doing a load store operation, you are going to use the data memory. So, you can't use the same memory for both instruction fetch as well as data fetch or data store. So, you need to have separate instruction and data memories. You cannot use the same functional units. And remember that you will have to use multiplexers wherever alternate data sources are needed for different instructions. So, this is the data path for your R type load and store instructions. So, as I indicated earlier, you have the instruction coming here, the instruction gets decoded, and based on the instruction getting decoded, you will have to that will go to the control unit and decide the various generate the various control signals. Meanwhile, because it performs a fixed length encoding, you read this register specifier, you read the second register specifier, you read the register into which you have to write the final result into, and then you have your ALU operation here. So, one register specifier is given here, register value is given here. The second input to your ALU either comes from the register specifier or it comes from the sign extended value. That depends on whether it is an immediate instruction in the case of a R type instruction, or if it is a load or a store instruction, the sign extended value gives the displacement. So, it is this value that is to be added to the base value if you have to find out the effective address for your load store instruction. And once that is done, and also for a branch instruction, it does the zero calculation, and once the ALU gets all these inputs, the ALU produces a result. Now, this ALU result may either be the address, that is for a load store instruction it is an address, for an arithmetic operation it is the ALU result, for a branch branch instruction you will have to produce the target address once your condition is satisfied. And for a load or store instruction, the address is given here, a memory read operation is given for a load instruction, the data is read and given here, or for a write operation a memory write signal is given, the address is given, the data is passed on here, and you will have to do a write operation. So, this shows the data path for a R type of load or R type load or store instruction. So, this gives you the full data path where you perform the instruction fetch here, the decode and register reads are happening here. Once the register reads happen, you give it to the ALU. So, it performs either the arithmetic operation or it calculates the effective address for a load store instruction. It calculates the target address for a branch instruction based on the branch condition evaluation, and then you have the memory access happening for load store instruction, and finally, you have the write back happening. So, this is the data that is to be transmitted and the register that is to be written. So, that shows the full data path. So, to summarize, we have looked at the various steps in the execution of a complete instruction with MIPS as a case study. So, we know that any instruction, first of all you will have to fetch it, you will have to decode it, you will have to fetch the operands, you will have to execute the instruction, and then you will have to write the result. MIPS is a special type of architecture, it is a RISC architecture, a load store architecture. So, things get very simplified here. So, we have seen how the data path gets implemented in the case of MIPS for an arithmetic instruction, for a load store instruction, for a branch instruction, and for a jump instruction. Thank you.